Polarized sources in ASAP 2008 can be defined with more flexibility and capability than ever. Sources can be randomized in terms of polarization, ellipticity, or orientation, and they can be stored at any place in the system for subsequent reuse. A reference ray is used to define the base polarization state from which all other polarization states are determined. In this simple grid source, we have a diverging wave field, as can be seen by the varying ray directions. We used a base linear state to describe the polarization, and thus each ray has a linear polarization state, but with its direction determined by the direction of its ray vector mapped from the reference ray which was defined for the system. Let's examine the randomization of polarization briefly. In this example, we've randomized polarization using three different schemes. The first scheme is randomized ellipticity. So the ellipticity of each individual ray is determined at random. In the second case, we've randomized in orientation. So the reference direction for each ray's polarization state has been varied. And in the third case, we've simultaneously randomized both the orientation and ellipticity of the polarization state of the rays. In this particular randomized source, suppose we want to examine the polarization state using tabular data. The list rays command has been augmented with the polarization subcommand, and in this case, we want to look at the state in Jones vector space. So to do that, let's go over to the edge and take a look. We have the reference ray direction for each ray defined, and then we have the Jones vector, a complex vector, defined for each ray. Let's consider another case. In this case, a random emitter rather than grid source. Since it's an emitting type, the ray positions and the ray directions are randomly determined when the source is created. But now, the orientation of the polarization is also randomly determined for each ray. And if we wanted to take a look at this using tabular data, we might use list rays polarization, but using the Stokes vector expression for the polarization state. So let's take a look at that by looking over at the right edge of the data. Again, we have the reference ray direction or the reference direction for each polarization, and then we have its corresponding Stokes 4 vector to describe the polarization state. Let's look at an application of randomized sources in a real system. In this case, we have a dome which has a quarter wave plate conformally applied to it, and we want to look at the effect on the polarization field passing through it. So the states are roughly linear states going in, but with slight ellipticity variation and slight orientation variation. And if we take a look at the result after passing through that conformal Jones quarter wave device, we see effectively Maltese cross information in polarization states. The states are unchanged in the principal axis directions, and they're modulated along the diagonals. And finally, let's take a look at the expanded capability to store and reuse polarized sources. In this case, we're going to propagate a polarized source to a reference plane, capture it, and then reuse it. This is a lens focusing an unpolarized source through a polarizer to a reference plane. We capture the wavefront at the reference plane along with all its polarization information, and then we re-emit the polarized source, make another copy, and re-emit from a slightly different point, simulating a polarization ghost. So we go through a lens, through a polarizer, capture at a reference plane, detector 1, through another polarizer orthogonal to the first, and capture at a final reference plane called detector 2. And we take a look at the polarization throughput of the system, and we see two Maltese crosses interleaved. A small one from the source which was closer to the lens, a larger one from the source which was farther from the lens. And because of a twist in the source orientations about the z-axis, the Maltese cross has some energy interchange from one lobe to another, and in opposite directions because of opposite twist in the direction of the sources. In summary, polarized source definition and manipulation is more capable in ASAP 2008 than ever before. Sources are defined in terms of a reference ray which maps all rays from a common basis. Sources can be randomized in terms of orientation and ellipticity, and polarized source fields may be stored and re-emitted for subsequent reuse.